Okay. What? Okay. Well, got it. So let's start. Okay. So hello everybody. I'm Haoyu Li. So I'm going to talk about a very basic stuff, which is called positive linear system. It's a brand of the system in the linear system, which is always positive. But while I'm talking about that, you are maybe change your thought. It's not only positive output give you the positive system. Okay. Okay. So the outline is that the first is a purpose. So where can we use the positive linear system? And the second, the definition of the positive linear system. So basic definition. So I will guide you guys as easy as possible and as clear as possible. And then the third is the observer. So I'm going to introduce the basic observer by like 1 or 2 minutes. So let you know that what's the requirement of the observer. And then I will going to switch gear to my positive observers. So this is a topic in 10 years ago or today. So you have a positive linear system with a positive observers. So what is the meaning of that and how do you achieve that? Because if you have observer, it's not very easy to get a positive one, you know. And the last one is the future work and conclusions. So what will we do in the future, or what can be discussed? Okay. The purpose. So why we need a positive system? So it's very straightforward because in the real world, basically everything is positive. The number of people, right? So like the population is positive all the time. The amount of water, amount of like fire, it's all positive. So there's not like a -3 grams of water, which is impossible, right? And then the concentration of the solution. So when you're like adding some chemicals, right? And in the output, you get concentration of solutions. So the concentration always is positive. This is impossible to get a minus concentration. So the positivity of the output is very interesting. And then the distance you travel, so your distance is always positive if you forget about the displacement. And etc. So basically, there are a lot of things in the world that is positive. Okay, so yeah, and so having a positive system, right, is a call of nature. It's basically the nature is a positive. So maybe something is negative. Let's say you can have negative, let's say the voltage, but in the other way, it's still the positive in the other way. You see, so and the definition of what system is positive. So how can I define this word positive? And so what is the definition of positivity of the system? So is that mean that if I have a positive of the output, so that system is positive? Sometimes it is, sometimes it's not. Okay, so that's a question mark. So and then the properties of positive system is very interesting because positivity not only give you the positive output, it will also give you very interesting progression of the output. So it's different from the normal one, which you oscillate. So the positive system will not oscillate. So there's some reason for that. I'm going to tell you guys that later. Okay, keep going. So the first definition of the positivity. So the linear system is said to be externally positive if and only if its force output is non-negative for every non-negative input. So for simplify that, so basically you have an input U which is positive and you get the positive output, right? So this is that simple. So if you have a positive U, you have positive Y. Okay, so example chemical concentration, so upstream. So this is graph I draw. This the U represent upstream. So this Y represent downstream. So if you have something positive, you have something positive on the downstream. And then total number of people get PhD who get a high school education, so etc. So there's a lot of examples for that. So this one is very interesting. We are going to recall that later. And but however, by using this this definition, there are two remarks. The first remark is that we could decide a sign. Okay, we could assign a positive sign to the inflow. And we can have a negative sign to the outflow. That means that we can change our sign by ourselves. So we can have the positive input to always give the negative output. So that will give you not a positive system, but if you change the sign, it go back to positive system. So this is very interesting. We need to avoid that. Okay, so this is this is a thing we need to avoid by using more of the theorem or definition. Okay. The second one is there is this externally positive system in which the input and output variable can also take negatives. So there's an example. So there's a circuit. So you input the U as a current, and the output is a voltage in the Y. So if you put a positive U, you always get a positive Y. So in this one, very interesting. But you also can give negative current by taking the current, and you are going to get a negative Y or positive Y. Okay, so the positive system can also input negative, but the result is unknown. That's the kind of stuff. Yep. So need more theorem to be needed to support this definition. So within the theorem, a linear system is externally positive if and only if its impulse response is non-negative. So what is meant by impulse response? So this is a definition, which is a proof, a short proof. So the impulse response is that, let's say you have upstream and downstream. When you add a single drop in the upstream, either going to result increase in the downstream or result a decrease of downstream. So that impulse of one drop is going to increase. If the increase of one drop of upstream is going to result in increase of the downstream, that system is a positive system. That makes sense, right? So basically, first, you need to have relationship between the U input and output. So input, we call that the U data, U tell. So it's the impulse. These are like really tiny of time. So very tiny input force. So like you can assume that's a drop. And then the YT is the output. So this is HT is a transfer function, which is E psi AB, right? So you all know that, so I don't need to talk about that. So this is a transfer function. So you transfer, so by using little amount of T, do you get increase of T by using increasing of U? So if this is satisfied, if H is non-negative, right? And then Y is non-negative for every non-negative input. So this is a additional theorem. Okay, too much time. Okay, now decide by, so there's example. There's a network, and then there's a, so I already calculate ABC in this case. And then for eigenvalues, so you are going to have eigenvalues A plus or minus root B. So if the B is positive, right, you are going to get two real eigenvalues. So in this case, you are going to have this solution like this. And then the H0, which is you take everything 0 as T, and the H0 is 0, as you can see from that, you calculate that by yourself. And then you get this result. And H dot 0, which is a change of the gamma matrix, is it's R over LC, which is always positive. So that because the H of 0, H dot 0 is positive, and then the H0 is positive, so the H is always positive. So therefore, when you have an impulse of positive value, you get a positive output. So this is, so when B is greater than 0, which you have two eigenvalues, you are going to have a positive linear system. So, but if the B is minus 0, this is very interesting. You get a pair of complex conjugate, which is A plus IB. Okay, and then if this happens, there's some. This is not. It's not external positive because the input response is occasionally changing. So it's like a sine function, which is not we are going to have. So I plot this in MATLAB, so you can see that. So in case 2, this is a 2 eigenvalue with conjugates. So you see there's an impulse when there's a increasing. So case 1, you see there's a very smooth and increasing. So when the increase of the du is always increase the yu. So yt. So it's always increase and then it stops. Okay, there's not the impulse place. So however, in case 2, you have this impulse, which is caused by the conjugate. So I something like 2 plus I 3i. So basically, so this causes that. So in this point, when you have an impulse of the input, you are going to have negative y. So this is not a positive system by the definition we just have above. So for for the b, if greater than 0 is positive, in the other way it's not. Okay, that makes sense. Okay, definition. So moreover, we have definition for external one, but we still need the internal one because we want to make positive. Positive also means the externally plus the internally. So we want them to be true together. Okay. So the definition for that is Li system is said to be positive if and only for every non-negative linear state and for every non-negative input, its state and output are all non-negative. That means if the U is positive and x1 is positive, x2 is positive, and y is positive. Okay, so everything is positive. Okay, that makes sense, right? So for the externally, we don't care about x1 and x2. It can be negative. We only care about y, but internally we need the x1, x2 both be positive. So in this case, so we care about amount of water in each lake. So we also we not only care about the downstream. Okay, so there's a graph explanation. Okay, in these two systems, so this is x1, this is x2. So this point is always stay in the x1 and x2 and the first quadrant. So the value of x1 and x2 are always positive. So this situation is a positive linear system. So but in this one, so it starts here and then it's always stay at the first quadrant. So that means that this is also a positive system. Okay. However, in this case, you see there's negative x2 here, right? But the trajectory is that this curve is coming from the fourth quadrant to the first quadrant. So when it enters when the x2 is equal greater than 0, it's never less than 0 in the future. So if you're going to trap it, in this case, this system is still positive because if the initial point is 0, so if the initial point and the further point is 0, it is positive. So we don't care about the point before it. Okay, so you basically trap it. Okay, so selection. So however, this still have a problem. So the selection of bases is also very important in this case. So let's say your selection of bases, the x1 is the amount of water in the lake 1, and the x2 is the amount of water in the lake 2, right? So those two numbers are positive. So however, you can also change your bases to z1 and z2, where the z1 is the summation of x1 and x2, and the z2 is a difference between lake 1 and lake 2. So in this case, the z2 can be negative, but the system is unchanged. So there's a graph explanation is like this. So in the first case, so x1, x2, the range of x1, x2 is all in first quadrant, which is all positive. And the second case, so your z1 is always positive, and by your z2, the difference can be negative sometimes. Okay, so this gives you some trouble. If this case is happened, it is not a positive linear system. Okay, so to have further mathematical meanings, you need more additional theorem. Still, it needs a lot of theorem to support the definitions. Okay, the theorem. Oh, sorry. Okay, this is a theorem. The discrete time linear system is positive if and only if the A and B and C are all positive. Okay, so this is I'm not going to prove it, so it's very lengthy. So a continuous time linear system is positive if and only if the matrix A is a measure matrix and the B is positive and C is positive. So the mirror matrix is defined as these non-diagonal elements are non-negative. So if you have a matrix and you non-diagonal, all the elements other than diagonal one are all positive, this system must be positive. So this is the definition. So the single proof, so very quick proof is that, so for x equals 0, x dot equals 0, equal to bu, right? So when the b is increasing, x increasing. So you want x dot to be greater than 0. So that means you have to make the u to equal to or greater than 0. So your b is greater or equal to 0. Okay, same for the c. You just like because your y is 0, right? So your y dot to be greater than 0. So and then you imply that the c must be greater than or equal to 0. And then the interesting part is that the mirror matrix. So the A matrix in this system must be measure matrix. So in this case, so this is still a lengthy proof. I don't want to go through that. It takes some time. Okay, so the idea is that when you have this, assume you have this the 2x2 system. So if you are only focused on x0, so the x dot 0 you want this one to be greater than 0 if your x1 is 0, right? So if the x dot 0 equal to, let's say this is a negative number, and then times x2 0, assuming x2 is a positive. So the x dot 1 is going to be negative. So therefore, your x1 is going to be negative. So that's not the thing we want to have. So to prevent that, we want to have the order of diagonal to be non-negative. So we can make it as 0, and we can make it as, let's say 1, 2, 3, 5, all positive values. Same for the x2, right? You want to make the a2 one as positive, because so this is this x2 changed by itself. We don't care about that. So if this is 0 and you want to have the dot change of the x2 equal greater than 0, you want to make the off diagonal one to be positive. Yes, that's a proof. Okay, so quick proof. I don't have. Okay, so what's observer? So that's the basic idea of the positive system. That's it. So everything should be positive, and then the A matrix should be a matrix. So you can see that by you have a matrix that if the off diagonal is all positive, this system is positive by itself. So the reason is very simple. So okay, so another question is that so you want to have an observer. So what is an observer? Okay, in general. And then I'm going to talk about what is a positive observer. So this is interesting, but I need to stay in the observer first. And then, I want to how to change the negative observer to a positive observer. Okay, how to change the non-positive observer to a positive observer. Okay, this is still interesting because you want everything to be positive in this case. Okay, so general idea is that you want the U feedback. You want some feedback in this way by Y, and you want feedback to be negative x hat. So you want to have a estimate x to feed back to the U. Okay. So you want to have something like this, and you want the y to be the input, and you want to have the estimated x in this way, and then you minus sign. Sorry. So you want to minus this to make the input as minus x hat. So you want to have an estimated state which is the same state as that, but it's not the same. So you using a y to get the estimate state of x. So this is a so-called observer. So everything that inside is called observer. Basically change the y to x hat, which is want to be as same as x. So how to make it? So basically it's very simple. So first you have a copy. Okay, so make a copy of the original system. Dynamics are the same, and then you just to plus how wrong your prediction is. So how wrong is the yt, okay, minus the cx dot t. So basically, this is how wrong your prediction is. So cx hat is a y hat, which is your prediction. So your actual value minus your prediction, you times some constant, and then you add into it to changing it until it's better and better and stay the same. Okay. So this is a step. So this is called predictor-corrector. Okay. So simply by having a copy and then plus error and adding how wrong your prediction is to the model. Okay. How to find observer gains. Okay. So I'm going through it faster. So assume there's a error x minus x hat. Okay. So E dot should be x dot minus x hat dot. In this case, so I'm not going to calculation. So in this case, in the end, you are going to have a E dot equal to A minus KCE. So you want to make the error as small as possible. And so therefore, you want to make the E dot as how to say it? You want to make the E dot stable as to 0, right? So you need to have this A minus KCE matrix to have negative real part. So not this one. You need to select the K to make the A minus KC have negative real part. Okay. So in the end, you are going to get this, and you have driving force of Y, and you have a itself. Okay. The error function. So I just graph it in this way. So I take the A like this. So which is the blue line. This is the original system A. So the orange line is a predicted line. Okay. So the predicted matrix is the K is 1 over 3 minus 2, 1, and the A minus KC equal to 1 over 3 minus 1, 1, minus 1, minus 5. So you can see that by definition, so this is obviously, okay, a positive system. Why? Because of diagonal, they're all positive, right? So it is obviously a positive system. So you see this green line, sorry, blue line. So the progression of blue line never overshoot. So it's increasing, 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 and then it keep increasing to its point. Okay. However, when this A minus KC, this one, this obviously a non-negative. This is a non-negative input linear system. So you see this order line, right? So in this case, so its x value become less and less compared to the former point. So this is valid, the definition of the positive linear functions. Okay, but this one is good, so we don't care about this one. But so it is wrong at here. So if the system is a positive system, it's never have this overshooting behavior. So this is what I learned in this positive linear system stuff. Okay. And then positive observer. So positive observer is very interesting because you want the observer to be positive and you want system to be also positive, or vice versa. So positive system, basically you are making a positive observers. So the observer matrix, which is A minus KC, is positive. Okay. So for this theorem, just go through it. So just give me a matrix A, which is only the matrix, and the non-negative matrix C, which is starting point. And then you have a K, so the K need to be like this, according to the paper, right? So K need to be this to be a positive. So therefore, you can have a positive Miller matrix A, observer matrix. You can have a positive observer matrix by having this kind of K. And then you just check if there's a K that can make the lambda O less than 0, okay? So if the lambda O less than 0, that means the error function is asymptotically stable. So therefore you can have a very good estimate of the original state. Okay, so the start is like you start with positivity and you go find the K, right? And then you just find the entire K that can make this true, right? If you can find the positive observer, you can find the K, okay, you got the positive observer and your job is done. Okay, that's easy, okay? However, it's not always the case. So for example, let's say you have a positive system like this, right? Positive, positive, all positive, all positive. So from this theorem, the last slide, we conclude the condition of K's are K1 greater than minus 1, K2 equal to 2. But there's no K that is satisfied for lambda that is less than 0 because there's always a lambda that is equal to 0. So it's impossible to meet this meet this one. Lambda is less than 0 because there's one equal to 0, right? So no, that's not a good idea. Right? That's not a good sign, right? So the error function is not stable in this case because your lambda is not negative, so it's not stable. So that means you are not able to get a positive observer given by this positive linear system. However, there's a way to fix it. Okay, so there's always a way to fix it. So let's give a K. So the lambda is the first priority because you want to make a lambda become true, and then you just make the K accordingly, right? So you want to make the lambda less than 0 first. So we just take an arbitrary K1 equal to 2 and K2 equal to 4 to make a lambda as minus 1 and 2. So it both negative, so they're extremely stable in long run. So, and then we substitute that. Okay, and it's obvious that, so this statement is not the positive because this is negative 2, right? You want to this be positive, right? So it's not positive. However, if you can transfer this system by T, this T here, by this T, right? You need to transform as T transfer, and then you transfer the case. After that, so you get a Z matrix, which is a positive linear observer. So the positive linear observer can be transformed from a non-positive linear observer by using a T this way. If you cannot, impossible find the one using the traditional way, you can have this alternative way based on the traditional way, like this. So this positive system, 0, 0, right? Positive, positive. Oh, that's right. This is a positive system. Good. Okay. Smell. So in the paper, this first matrix is denoted as F. The second one denoted as G. Okay. So you can just think about that. If you have a system like this, you can always have a transportation matrix which transfer z to x. And then you can have all things on the positive side, okay? That's a common idea. How to find the matrix? Okay, there's always theorem, okay? So there is if fg and t, so fg and t is to find that new one, and t is a transfer matrix, okay? So you just find the f, that is Hertz, and the Mercer matrix, and then you just solve the t, okay? It's just solve the t, that's it. And then you just see if the inversible of the t is positive. So if the t is t inverse is positive, you got it right, and it's non-singular, you are right. So start with positive controllable system, and FA don't share the same eigenvalue, so they can have a unique solution. And then you solve unique t, right? And then you check if the t is non-singular and t minus 1 is positive, okay? So if it's not positive, you go back this step and we choose another F and G pair, and then you just keep going until you find the t that is positive when you inverse it, okay? Then you're done, okay? This is everything, this is what paper have. So more mathematical problem is denoted in the paper that is there always exists F and G to make the opposite positive? So they are discussing that. If you're interested, go read the papers. Okay, what is the properties of T such as T minus T inverse is a positive matrix? So this still have some mysteries that we don't have a solid definition of T that make T inverse positive matrix. Okay, what will be the solution to some special cases? Like there are a lot of special cases denoted in the paper which need a lot of effort to use alternate way to find a t. Okay, finally, I'm done. Okay, so the positive link system is important part of lives, right? You want everything to be positive, so you want a positive system, and then you also want a positive observation, and then the positivity not only give you the importance of everything is positive, but also give you that the positive system is never overshooting because of the definition. Okay. Yep. I think that's all. Yep.
Very good. Very good. You use lots of examples. That's very good. Yeah. The key problem is the positivity is for continuous time. It's related to this metric is called a Metzler matrix. Yeah.
Yes.
So do you have any questions? Positive system. So the question from Kevin would be, is there a positive periodic system?
That's hard because if you have positive, you are not able to periodic because you need to go back. So if you want positive, you cannot periodic.
Well, I think you can have a periodic, right?
I mean,
you can do.
positive.
Why not you guys have a conversation and write a paper on this topic?
Well, I mean, you can make a very simple example, just sin x plus 1.
No, if you have that, you are going to have a negative impulse,
Okay, whatever.
But I feel like there's a possibility because you yourself is a positive periodic system, like your heartbeat, like your blood, like the calcium cycle every day. It's a periodic, it's positive, So I believe there must be something already there. So we're not doing research here. We just try to motivate people to think beyond the linear multivariable control course we have just learned. So I want to convince you that you are ready to fly. You already took off, okay? You are ready to fly, do some good research with linear multivariable control as the foundation. Any other questions here? I think we have kept you here for too long. It's almost 6. I'm going to thank everyone. Did a good job for the whole semester, and that's all for this course. It's not the end, it's the beginning of your academic journey. Hopefully this course is useful for your research. So stay in contact, and I'm very happy of about all your performance. So good job. So I'm going to end the meeting if you don't have further questions. Okay. Okay. Bye bye.
Okay. Thank you again.
Okay. Bye bye.
Thanks for inviting me.
Mhm, mhm.
Thank you.
Bye bye.